Imagine a massive, fast-moving river forcefully absorbing smaller tributary streams. The main current takes on the volume of the tributaries, but its overall composition remains entirely dominated by the initial flow. This is precisely how information travels through a modern deep learning model. The mechanism driving this flow is the standard residual connection. By simply adding a layer's input to its output, this equation provides a direct mathematical highway for gradients to flow backward through the network, enabling the training of extremely deep architectures. That gradient highway is its primary function. But if we examine the equation closely, we find a secondary, heavily overlooked role. The residual connection acts as a rigid, depth-wise aggregator. If we mathematically unroll this equation, the hidden state entering any given layer is actually the sum of the very first token embedding plus the outputs of all preceding layers. Notice the implicit coefficient of 1 in front of every single term in this summation. Because of that uniform coefficient, every layer receives the exact same, equally weighted sum of all prior layer outputs. The network forces a blunt accumulation, completely ignoring whether the data from layer 4 is more relevant than the data from layer 10. Standard residuals lack any mechanism to selectively retrieve or suppress specific information from the network's past. They simply stack everything into a single, unweighted pile. This piling effect becomes destructive when paired with prenorm, the dominant practice of normalizing data before passing it into a transformation layer. This chart shows the hidden state output magnitudes across the depth of a standard language model. Because prenorm normalizes the input, but the unweighted residual continuously adds new data, the mathematical consequence is that the hidden state magnitudes grow continuously at a rate of O of L as they move deeper into the network. To have any mathematical influence over this massive accumulated residual stream, deeper layers are forced to learn increasingly explosive output values just to register a signal. Conversely, the precise details formulated by the earliest layers become completely buried, diluted by the sheer volume of the accumulated state above them. We have seen this exact architectural bottleneck before. Recurrent neural networks, or RNNs, an older architecture that processed data sequentially, step by step, suffered from a nearly identical flaw. RNNs forcefully compressed an entire sequence of distinct tokens into a single fixed-size state, inevitably losing early context. Transformers solved that sequence bottleneck by introducing attention mechanisms. To solve the prenorm dilution problem, we need to apply that exact same logic to the depth dimension, replacing fixed residual addition with an attention mechanism over the network's depth. The architectural fix for this is called full attention residuals. We replace the fixed summation equation with a softmax attention operation. Softmax is a mathematical function that normalizes a list of numbers into probabilities that sum exactly to 1. Now, instead of adding everything equally, the model assigns specific probability weights to prior layers. To generate these weights, the architecture assigns a single, learnable pseudo-query vector to each layer. This query vector scores every preceding layer's output to determine its relevance for the current computation. Previous attempts to regulate the residual stream, like gated highway networks, required complex matrices. This mechanism requires exactly one single vector per layer. Depth-wise aggregation shifts from a blind accumulation into a fully selective, content-aware, and input-dependent retrieval process. During standard single-machine training, this modification adds virtually zero memory overhead. The intermediate layer outputs required for this attention operation are already kept in memory for backpropagation, the algorithm used to calculate weight updates by working backward through the network. Full attention residuals are mathematically flawless on paper, but deploying this logic in modern, large-scale distributed training environments introduces a severe physical constraint. Trillion-parameter models are too large to fit on a single chip. They rely on pipeline parallelism, splitting the network's layers across multiple physical GPUs. To save memory, the system dynamically clears and recomputes intermediate activations. Under standard pipeline parallelism, when one GPU finishes its set of layers, it transfers exactly one fixed-size hidden state across the network interconnect to the next GPU in the sequence. Full attention residuals break this system. Because layer 50 needs to attend to the specific outputs of layers 1 through 49, the system must keep all individual layer outputs alive and actively transmit them across the strict physical boundaries between GPUs. This creates an OLD bottleneck, meaning the memory and communication costs scale linearly with both the number of layers, L, and the hidden data dimension, D. As the model gets deeper, this ever-growing block of cross-stage transmissions scales up until it completely overloads the interconnect bandwidth linking the hardware. An elegant mathematical theory cannot survive if it shatters the physical constraints of distributed training. Deploying depth-wise attention requires a strict systems-level compression strategy. The engineered solution to this hardware bottleneck is called block attention residuals. Instead of attending to every single prior layer, we mathematically partition the total number of layers into a smaller set of discrete blocks. First is the intra-block accumulation. Inside a given block, the system acts normally, reducing the layer outputs into a single partial sum using standard unweighted residual addition. Next comes the interblock attention. The learnable softmax attention weights are applied only across the completed block-level summaries, rather than every individual layer in the network. This simple partition slashes the required cross-stage representations. Instead of maintaining hundreds of individual layers, the system tracks only a handful of block summaries, explicitly dropping the memory and communication load to a manageable level. There is one critical remaining infrastructure hurdle. Modern pipeline schedules use multiple virtual stages per physical GPU to maximize utilization. Left unoptimized, the system would repeatedly broadcast these block representations, wasting bandwidth. We explicitly eliminate this redundancy through cross-stage caching. Blocks received during earlier virtual stages are held locally in secure memory. On subsequent passes, the system securely transmits only the new incremental blocks that were explicitly computed since the last active exchange. Because the pseudo-queries are completely decoupled from the forward pass, interblock queries can be batched simultaneously. This enables a two-phase online softmax operation that drops the overhead during inference, the phase where a trained model actually generates text, to near zero. Block attention residuals successfully thread the needle, delivering explicit depth-wise attention without violating the strict memory and input-output limits of pipeline parallelism. To test this architecture in production, we evaluate a 48 billion parameter language model utilizing a mixture of experts design, an architecture that routes data to specialized subnetworks, activating only a specific subset of its parameters per token. This model was pre-trained on 1.4 trillion tokens. This chart shows internal hidden state magnitudes. The baseline model's magnitudes explode linearly due to prenorm dilution, but block attention residuals form a perfectly stable sawtooth pattern. Selective attention at every block boundary explicitly resets the accumulation, confining exponential growth and protecting early layer data. This chart shows how the gradient distributes across the depth of the network. The baseline model exhibits a massive spike in the earliest layers. Because standard residuals use fixed unit weights, they provide no regulation. The earliest layers end up monopolizing the gradient flow simply by structural default. Block attention residuals solve this. The learnable softmax weights force the layers to actively compete for probability mass. This naturally regulates the gradient, yielding a perfectly uniform distribution across the entire depth of the network. The empirical telemetry recorded inside the model aligns exactly with the math. The unweighted residual bottleneck is solved at scale. This chart shows the model's scaling laws, predicting performance based on computing power. The block attention residual curve shifts cleanly downward, achieving lower loss. Mathematically, it matches the exact loss of a baseline model trained with 25% more raw compute. Because later layers can accurately retrieve specific earlier representations, the model demonstrates outsized gains in complex compositional logic and multi-step reasoning. In downstream benchmark testing, the modified model recorded a 7.5-point jump on GPQA Diamond and a 3.6-point gain on math, proving that the structural changes to the residual stream directly improve reasoning performance. When looking back at the entire history of deep learning, true progress always relies on systematically breaking these structural compression bottlenecks. The transformer architecture took over the world when it proved that sequential recurrence was a flawed bottleneck, and that sequence attention was the correct mathematical path forward. Block attention residuals apply that exact same proof to the y-axis. Softmax attention is the optimal mechanism for sequence, and it is the definitive solution for network depth.